do for a moment is consider the possibility of ordering a pizza. And in this particular case, I would like to suggest that maybe we're going to look at possible pizza combinations where we have 4 choices of crusts: flat crust, thick crust, cheese in the crust, or New York style crust. We have 3 choices of a meat topping: ham, pepperoni, or sausage. Trying to keep things simple here. 5 choices of a non-meat topping: pineapples, peppers, onions, mushrooms, anchovies. And if we list that, and I will give you a little preview here, with 4, 3, and 5 choices, we're going to end up with 60 possibilities. Now that'll take a while to list them all, so I've invoked the use of a computer program. And here's what we have: our pizza choices. We have flat crust with ham and pineapples, flat crust ham and peppers, flat crust ham and onions, flat crust ham and mushrooms, flat crust ham and anchovies. And we've exhausted the flat crust ham options, so we move on to the flat crust pepperoni options, flat crust sausage options. And then you can see we just continue to list all the options until we're done with all the flat crusts. We're going to look at all the thick crust options, which goes back to the ham choices with pineapples, peppers, onions, mushrooms, anchovies, etc., etc. We get thick crust with all the pepperoni and all the veggies, thick crust with all the sausage and all the veggies. Then we list all the cheese in the crust options. Cheese in the crust with ham and all the non-meat toppings, cheese in crust with pepperoni and other non-meat toppings, cheese in crust with sausage, etc., all the way through the New York choices. So there's our list, and what we notice is that we've got some combinations. And so in certain situations where we consider combinations of items, which could be a succession of events like flips of a coin, drawing of cards from a deck, choosing pizza crust, toppings, or meats, each particular result is called an outcome. An event is a subset of outcomes: one drawing of the card, one flip of the coin, one choice of the pizza crust. And when several events occur together, like choosing a card followed by choosing a second card, or like our example, choosing a pizza crust followed by choosing a meat topping, and then of course followed by choosing a non-meat topping, we have what we call a compound event. And in a compound event, the fundamental counting principle comes to play. In a compound event where the first event may occur n sub 1 ways, the second event can occur n sub 2 ways, etc., the kth event would occur in n sub k different ways. The total number of ways for the compound event to occur is by multiplying all those choices as we go. N sub 1 times n sub 2 times n sub 3, etc. through n sub k. So as we look at that compound fundamental counting principle, let's look at it, applying it to this problem, trying to make it a little bit more simple than the pizza one. How many odd 2-digit whole numbers are there that are less than 70? Well, 2-digit numbers implies the fact that we've got a tens digit and a ones digit. And if it's less than 70, the tens digits has to be chosen from 1, 2, 3, 4, 5, or 6, not 0, because then it wouldn't be a 2-digit whole number. And it can't be 7, because it can't be equal to 70. It says less than. So that gives us 6 possibilities, 6 different ways in way the first event may occur. 6 choices, so to speak, also, if we look at it like that. Now for the ones digit, it says it must be an odd number. So that rules out, obviously, the even numbers and leaves us with 1, 3, 5, 7, and 9. And there are 5 choices of odd numbers. So if we now have a compound event, we chose a tens digit, we are now choosing a ones digit. Fundamental counting principle says to multiply those results together, and 5 times 6 is 30. So there are 30 2-digit odd whole numbers less than 70. And that's using the fundamental counting principle.